Okay, so hello everyone. We'll start the session in a while. So we'll just wait for 5 minutes so that some more people can join. Then we'll start the session. So just wait for 4 to 5 minutes. Then we'll start. Okay, we'll start the session now. For that, let me first introduce myself. So, my name is Himanshi Singh. I am currently a research scholar at the Department of Mathematics, IIT Jodhpur. I'm pursuing my PhD in a broad area of probability and statistics. Also, I'm your TA for the course Essentials of Data Science with R Software 2 Sampling Theory and Linear Regression Analysis. So, this course is taught by Professor Shalab on the SWAM portal, and I'm the one who's taking the live sessions each week. So after every week, when the content is there uploaded on the swam portal, then after that I'm taking these live sessions. So this is our 11th live session. Okay, so we have completed 10 live sessions. Okay, and this is our 11th live session. Okay, and also this is our second last live session. So next Monday on 13th of April, we'll be having our last live session. So basically, this was a 12-week course, and for each week we had a live session. Okay. Okay, so this is the schedule. Apart from this, these are some important links. So the first one is the Google Meet link by which you can join the this live session. Okay, and the second one is the link to my channel. So by which you can like access the recordings of these live sessions. So I will be uploading the recordings on the YouTube on my YouTube channel. Okay, from where you can access the recordings. Okay. Apart from that, third one is the Google Drive link. So where I'm uploading all the PowerPoint presentations and the R scripts, which I'm discussing here in this live session. Okay. So these are the three important links by which you can access all the materials for these live sessions. Okay. Now, for the what about the planning for the live session? So basically, we first um, discuss the recap of the topics which has been covered already in the previous week. So, like this is our 11th live session. So, whatever the topic that has been covered in the 11th week content, so we will be discussing some of like the major things, the whatever has been discussed. Okay, so I'll give you a brief recap about it. And if there is something, so then I will be demonstrating that in R. Then we will be doing some of the practice examples. Okay, in order to enhance your understanding about the topic, theoretical as well as practical. Apart from this, if someone of like if any one of you has any doubt or something like that, then we can discuss that also. Okay, so this is about the this is the information about the live sessions. Now further we will discuss the topics which has been covered in week 11 content. Apart from this, if any one of you have any doubt, then you may ask. Okay. Otherwise, we'll start with the topics. So, in order to first of all discuss about what we have covered in the yesterday's class. So, yesterday we had a live session. So, basically, we were talking about the linear regression analysis, where we were taking one independent and one dependent variable. So that was basically simple linear regression analysis, where there is a linear relationship between two variables. Okay, and we want to fit a straight line basically into the data. Okay, but here now, and also there we have now what is the line? So in order to estimate the line, we have to estimate the slope parameter and the intercept parameter. So we have discussed two methods. That is the method of ordinary, the estimation by ordinary least square estimation, and also the maximum likelihood estimation, by which we found out the estimators of the regression parameters and also the estimators of the variance. So basically, we considered the error to be coming from the distribution, or the epsilon i's are IID, and they are coming from normal 0 comma sigma square. And we've considered the estimation of sigma square also based on the method OLSE and the maximum likelihood estimation. Apart from this point estimation, we also discussed the testing of hypothesis, and also we have also discussed the confidence interval estimation for these parameters. Okay, now the theoretical understanding we have developed, theoretically we have understood that how these intervals are constructed, basically what are the formulas, how the testing is happening, how what is the test statistics, how we are taking the decision. Apart from this, we have also taken the we have also we also have calculated the expression for the ordinary least square estimators and maximum likelihood estimators. But apart from this, we have also in the previous lecture we have discussed the that how to do all these things in R. So by using a single command, we can get all the outputs, uh, by which we can avoid all the calculations, which we are basically doing by uh, putting all the observations in the statistics and finding out the values and all those things. We can avoid it using the R software. So we have basically calculated. So we have considered an example where we have to calculate all the things, whatever the variances of the estimators, what was the confidence interval and all those things, what is the value of the test statistics and all those things for different hypothesis testing problem. We have calculated them manually. And also we have seen that for what are the codes by which we can get all those things in R. Okay, fine. So this was about the previous lecture, what we have covered already. Now if we talk about now, so yesterday also I've given a brief introduction about the multiple linear regression analysis. So today our topic of discussion will be it will be around this multiple linear regression analysis. What is the model, of how to estimate the regression parameters, how to estimate the variance, and how to so this is basically we will be doing using the ordinary least square estimation method, maximum likelihood estimation method. So these are the methods for point estimation. Then we further will be going towards the testing of hypothesis. Okay, then further we will go towards the confidence interval estimation for these regression parameters. So here we will be discussing all the same things for the multiple linear regression analysis. So basically, what is multiple linear regression analysis? So first of all, in the previous one, we have calculated, or we have considered the model where there is a one dependent and one independent parameter. Okay, now here, if in place of one independent parameters, we consider that the dependent parameter is dependent on more than one independent parameter, or sorry, not parameter, variable. So for example, if I have a variable x1, x2, xk, so such that the dependent variable y is dependent on this x1, x2, xk, then in such a way, so mathematically it is given like y is equals to beta 1 x1 plus beta 2 x2 plus till beta k xk plus epsilon. So basically this y is dependent on x1, x2, xk, and x1, x2, xk are the explanatory variable, or I can say they are independent variables. Okay, and the dependency is in such a way, so does that y is equals to it is in this form beta 1 x1 till beta k xk plus epsilon. So then we'll say that the model is the multiple linear regression model. So basically we have data. So basically x1 is a particular variable, x2 is a variable, xk is a variable, so and y is also a variable. So what we will do, we will collect some of the observations for x1, some of the observations from x2, some of the observation from xk. So then, and also we will have some of the observations of y1 of y. So in that sense, if I want to write, so I can write this model in the matrix form which is given below. So here, what is this? The first vector is the y1, y2, yn. So this is the observation for the variable y. Okay, this x1 1, x2 1 till xn1 is is an observation for the variable x1. Okay, x1 to x2 till xn2 are n observations for the variable x2. Similarly, x1k, x2k, xnk, the last column is n observations for the for the variable xk. Okay, then in the right hand side we have written this vector beta 1, beta 2, beta k plus epsilon 1, epsilon 2 till epsilon n. Okay, so these are the random errors. So this is basically the model, or I can say this is it is a matrix form, because here we have more than one independent variable. Okay, so here this model can also be written as y is equals to x beta plus epsilon. So basically capital Y here we are denoting it by this so basically this capital Y is this vector y1, y2, yn. Capital X is this matrix, that is the how many these are n rows and k columns, so n cross k matrix. And here this beta 1, beta 2, beta k is are the, so this is this beta is basically a vector beta 1, beta 2, beta k, and epsilon is a vector epsilon 1, epsilon 2 till epsilon n. Okay, so this is basically the model for the multiple linear regression analysis. Okay, now here, first of all, now further, if we have a model, then this is the model we want to fit in these observations. Okay, so what will be the values of beta 1, beta 2 till beta k, so that we get an we get a like a fitted model. So basically, and behind this, so since we have discussed the simple linear regression analysis, there we have used the method of ordinary least square estimation, where we have just minimized the summation of epsilon I squares. So same method will be used here also. So then we will minimize it with respect to this vector beta. Okay, so then we will get an estimate for beta vector. Okay, so now since we are getting an estimate of vector, so we will get the estimate or estimator as a vector only. Okay, so what would be that vector? So in the next slide here, so here this is the ordinary least square estimator of beta. So basically it is x transpose x whole inverse x transpose y. Okay, so this will be a vector. Okay, so this will be a vector. So this is an estimator for ordinary least square estimator of beta. Okay, so this is the estimator. So basically this x transpose x, so here this is whole x, and transpose will be, this matrix will be like x11 x21 till xn1, and just the rows becomes column, column becomes the row. Okay, so x transpose x whole inverse x transpose y, so this will be a vector. Vector will be b1 b2 till bk. Okay, so this will be the vector. So here, so this will be an estimator of, so this will be an estimator of beta 1 till beta k. Okay, so this is the estimator by minimizing the square of the, so this is basically summation epsilon I square, we are minimizing with respect to beta. Okay, so then we'll get this kind of an estimator. Also, an ordinary least square estimator of sigma square is given by this quantity, that is sigma hat square. So this is given by this, so which is basically nothing but, so if I want to write it, so it is basically summation yi minus y hat whole square divided by n minus k only. Okay, here one thing to notice, that here we have considered this model where we have not taken the intercept term. Here we are considering to be x1 x2 xk, and here we have not taken the intercept term. That's why it is coming out to be, here it is coming out to be n minus k. So if there is an intercept term beta naught, okay, also present, so there will be k plus 1 this regression coefficients. Okay, so then in place of k we will write k plus 1, so then it will become n minus k minus 1. Okay, so the basically the k is the number of the regression coefficients. Okay, so so this is about the ordinary least square estimator of sigma square. So this is given by this. Okay, and this is the ordinary least square estimator of beta. Okay, I hope this is clear. Further, the fitted linear regression model will be x into b. Okay, so this will be the fitted linear model. So basically x, we have this, and we have estimated this beta 1, beta 2 till beta k. So this vector we have estimated by b. So we'll put those values, this b, b1, b2, bk here, and we'll find out this values, that is x into b. So then, so this will be the fitted linear regression model. Okay, or I can also call it as y hat also. Okay, so basically if I want to find the fitted values y hat, so that will be nothing but x into b only, and here b is nothing. So what is b here? X transpose x whole inverse x transpose y. So same thing I have written here, x transpose x whole inverse x transpose y, and we just name this matrix as, if we name this matrix as H, then it will become hy. So only we have to do the calculation, nothing else. Okay, so this is the y hat. Okay, so basically we are calculating xb only. Okay, the estimated value, the estimated vector of the vector beta. Okay, now if we talk about the residual vector, so that is nothing but y minus y hat. So y is the observations. So okay, so this is y1, y2, yn. So whatever the observation y1 we have, we will subtract it y1 minus y1 hat, y2 minus y2 hat. So those will be the residual. So this is basically the matrix. Okay, so this is the matrix. So this is y minus y hat. So that is whatever the values of y's will be there. So basically it will be like y1, y2 till yn. So these will be the values here. Okay, minus. So it will be y1 hat. So that is nothing but what will be the y1 hat? Okay, so here this is the y is equals to x into b. Okay, so y1 hat. So here by this we will get uh, uh, so this is basically if I have this value x11 x12 till x1k. Okay, this till xn1, this till xn2, still xnk. Okay, and here we will have b1, b2 till bk. Okay, so now this y1 hat will be nothing but this into this. So that is summation x. So this will be what? x11 b1 till x1k bk. So that will be this y1 hat. Okay, and y2 hat similarly we can find out till yn hat we find out, and if we subtract it, then we'll get this residual vector. Okay, so that will be the residual vector. So you can also do all this. So this is basically in this way we'll get, or you can just calculate this matrix and just calculate the H matrix and just find out this I is nothing but the identity matrix. So that is 1 1 till 1 and 0. So this is basically the entries on the diagonal is 1, and apart from this it is 0, and this subtract this by this with h and just find out the product with y. So that this will be a residual vector. Otherwise you can also calculate the yi hats in this manner and just find out the difference, and that will be the residual vector. Okay, so these are the two ways by which, so if you have already found out this h matrix, then you can just find out I minus h and find out the product with y. Okay, so this is just a kind of a representation. You can find out in other way also. So this is about the theoretical things, that what are the estimators, how we can get it. Now how we can get it by using R. Okay, so if R software we consider, so first of all we have to check that, for example, I have an independent variable x1 till xk, and this y is dependent on it. Okay, now y is a dependent variable. These now the relationship between y and x1, the relationship between y and x2, the relationship between y and xk. So it should be linear in order to fit such kind of a model. Okay, so in order to check that whether the relationship is linear or not, okay, we have to we can find out using some of the commands in R. Okay, so first of all we'll just plot and see that whether the relationship is linear or not. Okay, so if there we have a large data and we want to find out that whether there is a linear relationship or not. Okay, if there is no really linear kind of a relationship, if the scatter plot is very much scattered and there is no linearity seen, then there is no use to find out the linear model in it. Then other models may fit into it. Okay, so for that matter, we just use this some of the commands in R in order to see that whether the relationship between y and xi is a linear or not. So we'll just see the linear relationship between y and x1, y and x2, y and xk. We have nothing to do with that what is the relationship between xi's. Okay, that is not our concern. We just want that is there a linear relationship between y and xi's individually. So that is important. So for that we have this command pairs, and here we write this tilde y plus x1 plus till xk. So this will give the matrix plot of the data. Okay, I'll just show it to you here. Okay, so let me consider some data. So here I have considered this data x1, x2 and y. So let us plot this, okay, by using this command pairs. So pairs tilde y plus I have taken two independent variable x2. So let me run it. So this way. So it is coming this way. Okay. Now here this is the graph. Okay. Here this is the so here it is y. Okay, and here this is x1, here this is x2. Okay, so here if I consider this to be y, this to be y, this to be x1, this to be x1, this to be x2, this to be x2. So this is a relation, the y with y, the scatter plot of y with y. So that is we are not interested, and the scatter plot will be nothing because the values are same. Okay, so and the scatter plot between y and this is x1. So we can see that there is a linear trend here. Okay, and this is with y and x2. So this is the graph with y and x2, and here also we can see. So this value and this value are little deviated, but if we can see there is a some kind of a linearity here. We can see, we can observe. So here data set, I have taken a small data set in order to make the calculation a little easy. Otherwise, if there is a big data set, then we can also see the trend in a much better way. Okay, so in order to check the linear relationship, we can use this command pairs. Apart from this also, we can use the command core plot to visualize the correlation matrices. So basically, if I have the correlation, the value of the correlation coefficient, so basically that tells me that the how the like if the correlation coefficient is bigger than 0.5, then we can say that the linear relationship between two variables is significant there. So there is a significant linear relationship between the two random variables. Okay, so for that also we can use this core plot command. So here x is whatever the data frame. Okay, so let us do that also. So first of all, for that I have to make a data frame actually. Okay, so let us first construct a data frame. Okay, df data dot frame y is equals to c. Okay, let us write it directly. Comma x1 is equals to this. Comma x2 is this. So if I run it, so now I got this data frame. Okay, now I'll just use the command or plot. So for that I have to install a package. So I had so we have also discussed this. So let us see whether it will work or not. Otherwise I think I have to call the library. So library or plot, I think. So let us try to do it. Otherwise I have to see. So see COR of df. So yeah. So this is shown. So let me show it to you in numbers actually. Comma method is equals to number. Yeah, so this is the correlation plot. So which basically show us that there is a so here this is a variable y. This is y. So the correlation coefficient is coming out to be 1. And so basically, so we are considering, so y and y are same. So there is a maximum linear correlation between two y and y. And y and x1, the correlation is 0.99. So we can say that there is a high correlation between a high linear relationship between y and x1. And if we consider y and x2, then we can see that here the linear relationship, like there is a negative correlation between y and x2, and the value is also very small. So the linear relationship is very less, and also it is negative. So y negative basically means that if we increase the y, x2 will decrease, or we increase x2, the y will decrease. So the relationship is kind of in opposite direction. Okay. So here it basically gives us an idea that there is a linear relationship between y and x1. The linear relationship between y and x2 is a little smaller. Okay, so this is smaller. Okay, so this may be because I have taken such a data. If so, in practical purposes, the data must show a good linear relationship. Okay, in order to fit the model. So otherwise also we can fit a linear model, but maybe in practical purposes it may be of a little less use comparatively. Okay, so this is basically the visualization which we got using the corplot command. Okay, now since we had for example, we had a good kind of a linear relationship between the dependent and the independent variable, then we will fit a linear model. So basically, if I want to fit a linear model, we have two dependent variables, two independent variables, and one independent variables. So the command, the command which we have used earlier, that was lm. So we have used lmy tilde x. Okay, now we have two variables. Okay, two independent variables, or for example, k independent variables. Then we'll write the command lm y tilde x1, x2, xk. So it will give us the fitted model. So basically, it will give us the values of the coefficients, the regression coefficients. Okay, so it will give us the fitted model. Okay, also the command coefficients lm y tilde x1, x2, xk, it will give us explicitly the coefficients. So basically, the ordinary least square estimators of regression parameters, that is beta 1, beta 2, beta k. Okay, and the command fitted dot values. Fitted dot values lm y tilde x1, x2, xk, it will give us the fitted value. So that is y hat it will give. And the command residuals lm y tilde x1, x2, xk, so it will give us the residual values. Okay, so the residual value, so basically we'll get a vector for a particular so basically y minus y hat we will get from this residuals. Okay, so for particular x1, x2, xk, we'll get y hat, and we will get y minus y hat. Okay, fine. So these are the commands in our software by which we can obtain. So now this command will give to us the multiple linear regression model which has been fitted into the data. Okay, further we'll consider what are the properties of ordinary least square estimators. So basically, as we have discussed previously also for simple linear regression analysis, that the ordinary least square estimators are unbiased estimators. Okay, and so ordinary least square estimators for the regression coefficients and also for the sigma square, so they were unbiased estimators. Okay, so here also the ordinary least square estimators are unbiased. Also, it possesses the minimum variance in the class of linear unbiased estimators. So basically, they are blue. So best linear unbiased estimators. So among the class of unbiased estimator, linear unbiased estimators, they have the minimum variance. Okay, and also the covariance. So now we have a vector. Okay, previously we had a simple, like we had b1 and we have b2. So for estimators for beta 1 and beta 2, or I can say beta naught and beta 1. But here I have a whole vector b. Okay, so the variance will be, so there will be there will be a relationship between, so they are the b1, b2 and bk are not independent, so they will have some correlation. So they will have variances of b1, b2, bk, and also they will have some covariance between b1, b2, covariance between b1, b3, covariance between b2, b3. So basically we have a variance covariance matrix. So that matrix is given by this quantity variance of b, that is equals to sigma square x transpose x whole inverse. Okay, now this matrix, so this covariance matrix can be estimated by this quantity sigma hat square x transpose x whole inverse. So x transpose x we will get from the observations x1, x2, x11, x12 till so the whole n cross k matrix, and the sigma hat square is nothing. We can use this estimate of this sigma square, so which we have discussed here. So this is the sigma hat square. So this is basically this value. So it will be a constant. Okay, the summation of yi minus y at whole square divided by n minus k. So it will be a constant, and we will have this with this matrix be estimated by this. Okay, so this is basically the estimated variance covariance matrix of B, which is the estimator. Okay. Apart from this, the covariance matrix of y hat. So the covariance matrix of y hat is sigma square h. So h I have already discussed. So this is the h matrix. So this is the variance covariance matrix for y hat, and this matrix can be estimated by using the sigma hat square in place of sigma square. So in a similar way, so sigma hat square we can obtain by using that summation yi minus y hat whole square divided by n minus k. Okay, so this is basically the estimate. Apart from this, ordinary least square estimators, we have maximum likelihood estimators. Now for the regression parameters beta 1, beta 2, beta k, so for all those, the maximum likelihood estimator is same, okay, same as ordinary least square estimators. But for the sigma square, we have the estimator as given by this quantity. Sigma hat square MLE is n minus k divided by n into small s square, and the small s square is nothing but this quantity. This small s square is this quantity. So this is small s square. So this is an unbiased estimator of sigma square. Okay. So this quantity. So this quantity will give us a, so if I do n upon n minus, so n minus k upon n into this quantity, so that will be the maximum likelihood estimator of sigma square. Okay. So this is about it. Now further we can talk about the testing of hypothesis and confidence interval. So if I want to test h naught, that is beta j is equals to 0. So we have this model y to be equals to beta 1 x1 plus beta 2 x2 plus till beta k xk. Okay, now beta j is equals to 0 if I want to test. So for example, I want to test that beta 2 is equals to 0. And in that case, whatever the test is, for example, if I know that, okay, the null is accepted. Null is accepted means that beta j is 0. For example, beta 2 is 0. So then I will just conclude that, okay, beta 2 is not that significant. So I may drop it and do the analysis further by dropping the beta 2. Okay, so in that sense, the analysis for this hypothesis is important. So if this beta, some of the beta j is there for which the null hypothesis is coming out to be true after testing, then we'll just drop it from the model and we will just further do the further analysis by dropping that value from the model. Okay, so this is the thing. So here, if this is basically the use of the testing of this hypothesis. Further, how to do the testing. So the test statistic is nothing but bj. So bj is basically the estimator by which we, so basically bj, so we have estimated the vector b, so which was b1 b2 till bk. So from that we can get the bj. So bj divided by under root sigma hat square. So that was nothing but summation yi minus y hat whole square divided by n minus k into cjj. So cjj is nothing but a jth diagonal element of the matrix x transpose x whole inverse. So from this matrix I can get the jth diagonal element, and I will just multiply it to this quantity, take the square root and divide that quantity by bj. Divide bj by that quantity, then I will get the test statistic. Okay. Now, if that value, mod of that value is greater than this quantity T alpha by 2 comma n minus k. So basically how can we calculate it? We can calculate it using this command qt 1 minus alpha by 2 comma n minus k. So this is basically, or we can also calculate it using the student table also. But if I want to use R, then I can use this code in R to calculate this quantity. And if this quantity, the mod of this quantity is greater than this quantity, then we'll just reject it not. Okay. And apart from this also, the p-value, if the p-value is less than level of significance, then we will reject the null hypothesis at that level of significance. And how can we get the p-value? just get that p value and also the values of the test statistics and the values of the standard errors of the individual estimates of beta 1, beta 2, beta k, and the residual standard errors by the same command as we have discussed previously, that is the command summary lm y tilde. So here, no, it will not y tilde x, as we are there in the multiple linear regression model. So it will be y tilde x1 plus till xk. Okay, so it will be like this. Okay, so by this command we will be able to get all the values in R. Okay. Also, the what about the confidence interval? So confidence interval will be bj. So this is the same quantity minus t alpha by 2 comma n minus k, which can be calculated by this command, divided into the under root of sigma hat square cjj, which I have explained already, and the sum of this. So this will be the confidence interval for beta j. Okay, so however, we'll calculate them also. So how to calculate this confidence interval in R? So in R, we will calculate it using this command confint. Object, in place of object, we'll just write lm y tilde x1, x2, xk. Okay, parameter, so I will just skip it, then it will give the confidence interval for every parameter, and we'll just specify the level to be here. So here it will be 1 minus alpha. So if I want to test 5% level of significance, then I'll write it here 0.95. So that is 1 minus alpha. Okay. Also, this command summary will give us the residual error, and also it will give the value of the test statistics, the p value, and all those things. Okay, so this was about that how to do whole analysis, which we have discussed for the simple linear regression analysis, how to do all those things in multiple linear regression analysis. So in R, the change is only that we just replace this y tilde x by y tilde x1 till xk. How so? K will be dependent upon how many independent variables considering. Okay. However, there is a major change in the calculation for the like manual calculation. There is a major change. Okay. So now in the example, we will manual calculation for a particular example as we have done before, and we'll just see that how our calculation is coming, and we'll just further use all those things in R, and we'll just verify that whether the our calculation is matching there or not. Okay, in this process, you will be understanding the theoretical aspect, the theoretical formulations, how to calculate all the things in a much better way. Okay, by using R, all the things are happening in the background, and you may not know that how the things are happening. So the motivation in order to consider the theoretical things or in order to do all the calculation is that you understand that how everything is coming. Because in R, you just write a command, you will get the output. Okay, but you need to understand and how the things are happening. Then you will have a better understanding for the topic also, and how to apply it or how to use those topics in R. Okay, so if there is any doubt or anything, then you just tell me. Otherwise, I will start with the question. Okay, so if there is no doubt, then I will start with the question. So, here in this question it is given that consider this data set first of all. So we have a data set where we have a independent variables to be x1 and x2. So we have two independent variables and one dependent variable y. Okay, so now we have some observations. So there are 5 observations we have. Okay, so let us first see that whether the like how the scatter plot for these or the matrix plot for these values is showing. So let me show that to you in R first. Okay. So basically, I have stored these values x1, x2, x1, x2, and y. Okay. Let me do this pairs command. So pairs command will give me the matrix plot. So this is basically the matrix plot. So you can see here the relationship between this. So this is y here, this is y here, this is x1 here, this is x2 here. So between y and x2 there is a linear relationship. So the linearity is visible. Between y and x2 you can see that there, like, if these points and these points, these 2 points are like they are not showing a linearity in the data, but these 3 points may be showing a linearity in the data. So the linear relationship is little less in this data. Okay, however, we'll just fit it. We'll try to fit that how the fitted line will be, I don't know, but in order to see that whether there is a linear relationship or not, so this command I'm making use of pairs. Okay, so this will show me this. And also if I want to see the core plot, the which will basically give us the visualization that how the linear relationship, how what and what is the percentage of linear relationship between the two variables y and x1 and y and x2. So for that, let me find out that graph by using core plot command. So for that, I have to construct this. So that is data.frame. I've constructed this, and I've called the library core plot, and I'll just find out the core. And in the argument, I attend CORDF. So basically, this will give the correlation matrix, and here the method is number, so it will give me the visual form of numbers. See, here we can see that y and x1, the correlation coefficient is 0.99, and y and x2 it is minus 0.25. Okay, so the relationship between linear relationship between y is higher. However, the between y and x2 is smaller, and also the relationship is negative. Like if we increase y, x2 will decrease. Okay, so this way we can see that how the data is behaving. Okay, we have seen that. Okay, now we will first try to fit a linear model into it. Okay, so in the question it is asked that on the basis of the given data set, obtain the fitted multiple linear regression model. So we want to fit a multiple linear regression model. So we want to fit y is equals to beta naught plus beta 1 plus beta 2 x2 plus epsilon. So we will have this. Okay, and we want to get, y is equals to b naught plus b1 x1 plus b2 x2 plus nothing. Yeah, so this will be the fitted model. Okay, now how to, so for that we need to find this vector. So we need to find the vector b, which is equals to b naught b1 b2. So this vector I want. Okay, so this vector I want. How to get this vector now? So we already have the estimator, the OLSE estimator for this vector, so which is given by this quantity, that is x transpose x whole inverse x transpose y. So let us first find out that what is our x here. So x is what? So the matrix x is, if I want to write, so here you can see that we are fitting this model. So here beta naught, the coefficient of beta naught is 1 everywhere. So we'll write the first values to be 1, 1, 1. Okay. And we have 5 observations. So let us write it in a smaller font. So it is 1, 1, 1. And the x1, the values of x1 is 1, 2, 3, 4, 5. So it is 1, 2, 3, 4, 5. Okay. 4, 5, 3, 6, 2. It is 4, 5, 3, 6, 2. Okay. So this is the matrix X. What is the matrix Y? Or I can say the vector Y. So the value of Y, values of Y is 10, 12, 13, 16, 18. 10, 12, 13, 16, 18. Okay, so now what is P? So it is X transpose X whole inverse X transpose phi. Okay. Yeah. This is inverse here. Okay. So let A be equals to X transpose X. So what this matrix will be? So this is equals to, so X transpose is 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 4, 5, 3, 6, 2. Okay, and X is the same. Okay, so let us find out this matrix now. So basically, you will do the matrix multiplication for it. So this into this, 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 and similarly for the third row. Okay, so then the A will be what? So then A will come out to be, so I have calculated that actually. So that because the calculation is little lengthier, so I just wanted to show you that how the calculation will go on. So let me show you. So what is basically this matrix will come? So this matrix will be 5 here, 15, 20, okay, 15, 55, 57, okay, 20, 57, and 90. So this is the matrix A. So which is basically X transpose X. Now we need to find A inverse. Okay, so which is equals to what? Adjoint of A divided by determinant of A. Okay, so now what will be the, so first of all, we'll just use, so what will be the determinant of A? So determinant of A will be 5 into 55 into 90 minus 57 into 57 minus 15 multiplied by 15 into 90 minus 20 into 57. Okay, plus 20 multiplied by 15 into 57 minus 20 into 55. Okay, so this will be the determinant of A, which comes out to be, so the determinant will comes out to be 455. Okay, so if you calculate this value, so then the determinant will come out to be 455. Okay, now further, if we have found out the determinant of A, we will find out the adjoint of A. So for adjoint of A, we have to find out the cofactor matrix. Okay, So basically, in place of the first entry, will in that matrix, the matrix C will find out. So that matrix will be in the place of first place. We will write the value this into this minus this into this. Okay, so we'll write this value in place of this. So here we'll write 55 into 90 minus 57 square. Okay, in place of this matrix, we'll write 15 into 90, 20 into 57. 15 into 90 minus 20 into 57. In place of this, we'll write 15 into 57. 15 into 57 minus 20 into 55. Okay, and now in place of this, we'll just leave this row, this column, this row. 15 into 90, 15 into 90 minus 20 into 57. 57. Okay, here it will be 5 into 90 into 20 ka square. 5 into 90 minus 20 square. Okay, and in place of this, we have 5 into 57. 5 into 57 minus 15 into 20. Fine. In place of this, we will have the same as this value, 15 into 57 minus 20 into 55. Okay. And okay, so here it will be same as this, 5 into 57 minus 15 into 20. And here it will be 5 into 55 minus 15 square. 5 into 55, 15 square. Okay, so this is basically the matrix, and which is symmetric also. The transpose will be same. So the A inverse, I can say, or I can say X transpose X inverse will be this divided by the determinant. So determinant is 455. So this is 1 upon 455. And if we evaluate it, so the values will be 1701. Okay, minus of 210. You can calculate these. Minus 245 minus 210, 50, 15. This is again same, minus 245. Okay, and this is 15, and okay, so let me write this in another page. So that is A inverse, that is equals to X transpose X inverse. So it will be 1 upon 455 into 1701 minus 210 minus 245. Okay, yeah, wait a minute. So here the signs will be like it is a first row, first column. So their sign will be positive. Here the sign will be negative. Okay, so it is not actually taking. So I'll just just informing you here. It is not taking. That's why I'm not able to write that here. The sign will be negative. Here it is positive because it is first row third column. Okay, here the sign will be in negative because it is second row first column. So similarly here it is positive, here negative, here it is positive, here it is negative, here it is positive. Okay, so in this way, by which only I am able to write the values like this. So it is -245 here, and then it is -210, -210. Okay, and this is 50 here. Here it will be 15, here it will be 50, here it will be 15, and here it will be -245. So this is coming out to be this inverse matrix here. And now what is B? So B, the next term was X transpose B. So let us find out X transpose Y, sorry. So the X transpose is what? So the X transpose is 1 1 1 1 1. Okay, 1 2 3 4 5, and 4 5 6 3 6 4 5 6 3 6 multiplied by y is 10 12 13 16 18. Okay, so this matrix will come out to be this multiplied by this, so it will be sum of this. So the sum will be, so 12 and 18, it will be 30 40, and 40 plus this is 6, this is 29, so it will be 69 here. Okay, this into this, so it will be 10 plus 24 plus 39 plus 64 plus 90. Okay, so it will be it is 90 plus 10 100 plus 24 and 64 88 plus 39. So this is 8 7, so it is 227, so it is 227. Okay, and the third one will be 4 into 10, that is 40, 12 into 5, that is 60, plus 13 into 6, 78, 16 into 3, 16 into 3, 48, plus 18 into 6, 108. Okay, so if we'll sum it, so it will be 4 carry 1 7 8 9 10 11 12 18 2 carry 2 okay 16 3 48. And there is a little difference here in it. So the so it is 60, 40, 100, 208 here plus 31, 126, and it is coming out to be 334. Okay, so this is it about x transpose y. Okay, now further, um, okay, I hope I'm visible. Yeah, so here further, so this is basically the x transpose y. Now we'll calculate b. So b will be, okay, so b will be the product of these matrix. So it is 100, 1455, sorry, 455, but divided by, and this matrix came out to be 1701 minus 210 minus 245 minus 210 50 15 minus 245 15 and 50, and here we'll have this matrix 69 227 and 334. So if there is any mistake, then please let me know, or you just correct it yourself if there is any mistake in the calculations. Okay, fine. So this is b now. So b will come out to be 7.26, 2.03 when you just divide it and multiply and divide it by 455, 0.11. So basically here it will give us these regression coefficients. So basically the model will be y is equals to 7.26 plus, okay, 2.03 x1 plus 0.11 x2. So this will be our fitted multiple linear regression model. If there is any doubt in this, then you may ask. If there is any doubt, then you may ask. Okay. So this was our fitted regression model, linear regression model. Further, in the question 2, it is asked that find the residual standard error. So the residual standard error. So it is nothing but summation yi minus yi hat whole square divided by n minus k. Now here I have this model. So here we have 1, 2, 3 regression parameters. So the value of k will be 3 here. Okay. So the value of k here, and n is one population, that is 5, and k is 3 here. Okay, now yi hats we need to find out. Okay, so now yi hat what? So if I have x1, I have the value of x2, then for that particular corresponding yi, the value of yi hat you will be able to find out. Okay, so let me write the values of y here. Okay, so the values of y are so the values of y are so the values of y are, sorry, so here it is 10, 12, 13, 16, 18. So it is 10, 12, 13, 16 and 18. Okay. And corresponding to what xi? So x1 and x2. Okay. So the values of x1 and x2 are so I have already written it there. So let us not okay. Just I will just do this. So now, so here, so we will find out the values of yi hat. Okay, the values of yi hat. Okay, so here we have this model with us. We'll put the values of x1 and x2 and we'll find out a corresponding yi hat. So the x1 value is 1 and 4 for y to be 10. Okay, so 1 and 4 we will put here. So if I put 1 and 4 here, so y, so basically y1 hat is equals to, so it is 7.26 plus 2.03 into 1, so that will be 2.03 only into 1 plus 0.11 into 4, 0.11 into 4. So that value we can calculate, so that value will come out to be 9.73. So this will be y1 hat. Okay, so this will be y1 hat, so it will be 9.73. Okay. Further, for the second value, this value, so the value of x1 is 2, x2 is 5. So 2 and 5 we will put. So y2 hat will be 7.26 plus 2.03 and here will be 2 and 0.11. So it will be 5. Okay, so this will come out to be 11.87. Okay, 2 and 5. So this is 11.87. Fine. Further, the third value is 3 and 3. Okay, so y3 hat will be, so this will be same, here it will be 3 and here it will be 3. This will be same. Okay, so now the value will come out to be 13.68. Fine, so it will be 13.68. Now y4 hat, so it is 13.68. Just 4 and 6 for the fourth value. So it will be 4 and 6, so 7.25 to 6, sorry, plus 2.03 into 4 plus 0.11 into, what is it? 6. 4 and 6. So this will come out to be 16.04. Similarly, y5 hat, it is 16.04. This is 5 and 2. So this is same plus this is same, this is 5 plus this is same and this is 2. So it will be, so it will come out to be 0, so not 17.63. Okay, 17.63. Okay, now if I find out yi minus yi hat, okay, so this will be this subtraction, this minus this. So this is 0.7. So if I find out yi minus y hat whole square, because that only we need. So that quantity will be what? So here this minus this whole square. So that will come out to be 0.27. Okay, that come out to be 0. So 0.27 will be the difference only of this difference of this square. It will be, the difference will be 0.27. Okay, this difference will be 0.13. This difference will be minus 0.68. This difference will be minus 0.04. And this difference will be 0.37. Now we need to square them and we need to find out their sum. So yi minus yi hat whole square will be what? So 0.27 square, let me do that. So 0.27 square. So it is 0.0729. Okay. 0.13 square. So it is 0.0169. Okay. 0.68 square. 0.4624. 0.04 square. 0.0016. Okay. 0.37 square. 0.1369. Now we have to sum them. So if we sum them, so here we'll write summation yi minus yi hat whole square. So that comes out to be 0.691. Okay. Now what we need to find out? We need to find out this quantity. So residual standard error small s square. So that will be 0.691 divided by 4 minus 3. So that is 2. So this will come out to be 0.345. Okay. So this is the estimate of the variance, and the standard error will be s. So that is under root of 0.345. So that is 0.58. So that will be your residual standard error. Okay. I hope this is clear. If there is any doubt in this, then you may ask. Okay, so if there is no doubt, then I'll move for the next one. So here it is asked that calculate the estimates of variance and standard error of individual OLSEs. So I want to calculate, so we have B naught, we have B1, we have B2, okay, 3 parameters we had. Okay, so we need to find out the variance. So what will be the estimate of the variance of B naught? What will be the estimate of variance of B1? What will be the estimate of variance of B2? Okay, so that will be what? This we need to find out the variances, and then we also need to find out the standard errors. For that, we need to find out first of all. So we had this thing that the variance covariance matrix of B. We had this variance of B. So what that was? So that was sigma square into X transpose X inverse. Okay, and if we want to find out their hat, so then we need to find out this hat. Okay, and this hat was nothing. This, in place of this hat, we just find we can write this value. So this will be nothing but s square into s x transpose x whole inverse. Okay, and these variances, the variances of this will be the diagonal entries of this matrix. Fine. So let us find out this first. So S square we know. So what will be the variance covariance, the estimate of variance covariance matrix? So S square is nothing but 0.345. So 0.345. We also know that what is X transpose X whole inverse. So that matrix was, so the X transpose X whole inverse. So this was that matrix. Okay. 1 upon 455. So that divided by 455, I can say. Okay. And the entries of the matrix were, so let me write it from my paper. So yeah, so it was 1701, okay, minus 210 minus 245 minus 210 50 15 245 15 and 50. Okay, and this calculation we can do, and further if we do this calculation, then we can find out these values. So what these values will come out to be? So these values will be what? So we need to calculate it actually. So let me do this. So it is 1701 divided by 455 multiplied by 0.345. So this value will come out to be 1.28 9. Okay, we only need the diagonal entries, so I will just calculate the diagonal entries. Okay, and here it is 50 divided by 455 divided by 0.345, 0.0379. Okay, and this again will be same because all the values are same, so 0.0379. So what are the variances coming? So it is coming out to be 1 point, so this is 1.289. Okay, this is coming out to be 0.0379, 0.0379, and this is again 0.0379. And apart from this, what will be the standard errors? So standard errors of B0 will be the square root. Standard error of B1, it will again be the square root. B2, it will again be the square root. So the square root of this quantity. So let me find out. Square root of 1.289. So it will come out to be 1.135. Okay, and the square root of 0.0379. 0.0379, so it is 0.1947. This will be same because the values are same. So these are coming out to be the individual standard errors and individual variances of BIs. And this is the variance covariance matrix for B. Here also these values can be calculated by this calculation. Okay, so this is the variance covariance matrix. Fine. Now further also we need to here calculate the maximum likelihood estimate of sigma square. So the maximum likelihood estimate of sigma square was given by n minus k upon n into s square. S square we know, k we know. So n we have 5, k we have 3. Okay, s square was what? So we have already calculated s square to be 0.345. You just put the value, so that is what, n minus k, so this is 2 upon 5 into 0.345. Okay, so what this value will be? So it is 2 into 0.345 divided by 5. So this is 0.138. Okay, simple. So it was a little simple. Now we'll move towards the test statistics. Okay, so if we consider beta naught to be 0, the null hypothesis against the two-sided alternative. So basically we are considering this hypothesis. So what will be the test statistics? So basically what is the test statistics for this? So test statistic is nothing but beta, so this is beta naught. So we'll consider the estimator of beta naught. So that is B naught divided by under root of here we will consider the variance of B naught. So that will be the individual standard error. So it will be the standard error of B naught, which we have already calculated here. This. Okay, so that is nothing but all only the s square, the under root of s square into the first diagonal element of x transpose x inverse. That only we have calculated here, 1.289. So that only it is coming. So here it will be the same standard error of B naught. So what the test statistics will be? So what is B naught first of all? So what is B naught came out to be? So B naught was 7.26. So here it is 7.26, and the standard error, so not the under root of standard error, it is standard error only, so that is variance of V naught. So variance V hat of V naught. So that is the standard error, so that we have already calculated, so that is 1.135. 1.135. So let us calculate this value. So it is 7.26 divided by 1.135. 6.3964. Okay, so this is the test statistics, and also we want to calculate 90% confidence interval. So alpha is here 0.10. Okay, and we need to, so what will be the confidence interval? So confidence interval is beta naught plus minus t alpha by 2 comma n minus k. So that is, so n is 5 and k is 3 here. So 5 minus 3, it is 2 degrees of freedom. Okay, into under root of variance of b naught, this hat. Okay, so this will be the confidence interval. So B naught value is 7.26. So confidence interval will be 7.26 minus this value alpha by 2, t alpha by 2 comma 2. Alpha is 0.10. So we can calculate it by using qt command. So that qt 1 minus alpha by 2, and alpha is 0.10, alpha by 2 will be 0.95, so it will be 1 minus 0.05, 1 minus 0.05 comma 2 degrees of freedom. So this is qt 0.95 comma 2. So let us see that what that value is. So this qt 0.95, 2 degrees of freedom is 2.919. So yeah, we'll use this value 2.919. Okay, multiplied by this quantity. So that quantity is 1.135. 0.135. Okay, and the sum 7.26 plus 2.919, 1.135. So 90% confidence interval for beta naught is, so let us calculate this value. 7.26 minus, so this is 2.919 multiplied by 1.135, 7.26 minus, so it is 3.946 comma, if we sum it, 10.573. So this will be our 90% confidence interval for beta naught at, okay, so for beta naught we have calculated. Further, if we go for beta 1, 95% confidence interval, then nothing, we just change the test statistics. So test statistics will be what? B1 divided by under root of variance of B1. So those things also we have calculated. So what B1 is? So B1 is 2.03. Okay, so this is 2.03 divided by what was the standard error we have calculated? 0.1947. So it is 0.1947. Fine. So this is equals to, so let me calculate this also. 2.03 divided by 0.1947. So this is 10.426. Okay. So this is the value of the test statistics. Now 95% confidence interval. So alpha is 0.05. So the t alpha by 2 comma n minus 1, and sorry, n minus k. So this will be obtained by command qt. Now alpha by 2 is 0.025. 1 minus alpha by 2 will be 0.975. So qt 0.975 comma n minus k. N is 5, k is 3, so it will be 2. Okay, so this quantity will be what? By r. So I have written it here, 0.975 comma 2. So it is 4.302. So it is coming out to be 4.302. Okay, now we will calculate the confidence interval. So confidence interval will be what? So this is 2.03 minus 4.302 multiplied by 0.1947, comma 2.03 plus 4.302, 0.1947. Fine. So what will be the 95% confidence interval for beta 1? So this is the value 2.03 minus 4.302 multiplied by 0.1947. This is 1.192, comma 2.867. So this will be the 95% confidence interval. Okay, so now in the next question, calculate the test statistics for the hypothesis beta 2 is equals to 0 and also calculate the 99% confidence interval. So for this, the test statistics will be nothing but B2 divided by under root variance of B2, which we know. So what B2 came out to be? So B2 came out to be 0.11 divided by what was the standard error? So this was 0.1947 only. 0.1947. So this will be what? 0.11 divided by 0.1947. 0.564. Okay. And 99% confidence interval means that alpha is 0.01. So alpha by 2 will be 0.005. Okay. So T alpha by 2 comma n minus k can be obtained by QT. 1 minus alpha by 2 is 1 minus 0.005. So it will be 0.995. Okay. Comma n minus k is 2. Okay, so let us see what this value came out to be. So it is 9.9248. So it is 9.9248. Fine. So 99% confidence interval for beta 2. It will be what? So it is B2. So this is 0.11 minus this value 9.9248 multiplied by the standard error, that is 0.564. No, not 0.564. What is the standard error? So 0.1947 in the sum. Okay, so it will be what? So let us do that. So it is minus 1.8154 comma 2.0354. So this will be the 99% confidence interval for beta 2. Okay, so this was all for it. Now we will just verify these things, these all things by R. Okay, so in R we will do and verify that whether the answers which we are getting, they are correct or not. Okay, so first of all, let us fit the model. Okay, so our model is this. Okay, and we'll just fit the model using the command lm y tilde x1 plus x2. Okay, so here you can see that the intercept term is 7.26, the coefficient of x1 is 2.033, coefficient of x2 is 0.109, and so here also we are approximately getting the same value, 7.26, 7.26, 2.03, 2.03 and 0.109, which is approximately 0.11. So this is the same thing. Okay, so the same model we are getting through this. Okay, fine. Now, further, we also calculated the residual standard error, and we have calculated the estimate of the variances and standard error of individual OLSEs. So for that, we'll just use the summary command. So let us calculate this. So this is summary lm y tilde x1 plus x2. So if we run it, so we get all these things. So here you can see that the uh, the coefficients are coming here, these values. Corresponding standard errors are here. So this is the standard error for this one is 1.1358. So this is also coming out to be 1.135. Okay. Here it is for the coefficient of x1, it is 0.1947. Here also it is 0.1947. And for the third one also we have the same standard error, and it is also 0.1947. Okay. Fine. And now further we have also calculated the residual standard error, so which came out to be 0.588. Here also we are getting the residual standard error to be 0.5874, approximately 0.588 only. Okay. Apart from this, the value, the t values is the value of the test statistics. So let us see. So the value of the test statistics we got. So this was for the beta naught to be equals to 0, means this is for the intercept parameter. So this was coming out to be 6.3964, and here also you can see this is 6.93, 6.39, sorry, 6.393. Okay. Next, for the for the coefficient of x1, for this one the test status is 10.426, and here also you can see it is 10.44, approximately equal. For the third one, for the beta 2, it is 0.564, and here also it is coming out to be 0.564. Okay, here you can see the p value. So p values for the first one is 0.02. So this p value is less than 0.05. So we will reject the h naught at 5% level of significance. But what about what about the 1% at 1% level of significance? So basically, when our alpha is 0.01. Okay, so at 1% level of significance, the p value is greater than 0.01 basically. So we will not reject at 1% level of significance. But since the p value 0.02 is greater than, sorry, less than 0.05, so at 5% level of significance, we will reject H naught. Okay. And for the coefficient of x1, we can see here it is 0.009. So basically it is less than 0.01. It is also less than 0.00, sorry, 0.05, but it is not less than 0.001. So basically we will reject at h naught. We will reject h naught if at 1% level of significance. We will reject h naught at 5% level of significance. But if we consider the alpha to be 0.001, then we will not be able to reject, because then p value is greater than 0.001. But okay, now for the third one, the p value is coming out to be 0.629. That is very higher. Okay, so this is very high. So it is also higher than 0.5. So that is 50% level of significance. So here majorly, so it is very high. So it is not less than alpha for a significant small alpha. Okay, so it is always greater than alpha. So we will always accept H naught for it. So we'll always accept H naught for it means that beta 2 is 0. Okay, here we are testing for beta 2 to be 0. And here it is saying basically that beta 2 is not that significant. So we can uh, we can skip this beta 2. So in the graph also we have seen that the relationship between the x2 and y was not that linear. Okay, so here it is saying that we can skip the beta 2 in the from the model, and we can just fit the to the model beta 1 x1. We just skip the beta 2. We can take the beta 2 to be 0. Okay, so from here also you can see that. Fine. So this is it, and let us now find out the confidence intervals now. Okay, so we'll use the CONFINT. So for the confidence interval, 90% confidence interval, if we find out. So we'll write this command confint lmy tilde x1 plus x2 label to be 0.90, and we got the confidence interval for all the three terms: intercept term, coefficient of x1 and coefficient of x2, that is beta 1 and beta 2. So these are the confidence interval, but we have calculated for beta naught only. So this is the first one. So let us check. So what was our confidence interval came out to be? So this is 3.946 comma 10.573. So this is approximately equal to this first one. So because we have calculated for this intercept term for 90% level of significance. Okay. So 90% uh, for like 10% level of significance. Okay. Now for the sixth question, we have considered 95% confidence interval we want to construct for beta 1 to be 0. So if we consider that, so we'll take the level to be 0.95. Now for the second one, the interval is coming out to be 1.195 comma 2.87. So here also we are getting the similar outcome. So 1.195 and 2.87. So it is approximately equal. Okay. And for the third one, we have calculated 99% confidence interval. So for that, we'll write level to be equals to 0.99. So if we see it for the third one, so the confidence interval is coming out to be minus 1.82 comma 2.04. So it is also approximately equal. So minus 1.82 it is coming. So here it is 815 and it is 2.035 and it is 2.042. So it is approximately same. Okay, so this is so in this way we can also obtain the confidence interval for these regression parameters for multiple linear regression analysis using R directly. We no need to do all the calculations. So here I have done the calculation to make you understand that how the theoretical foundations are working. So all these things has been coded inside these functions under the packages. Okay, so all these things are being coded, and directly by using this command we are getting all the outcome. Fine. So this was lecture. Okay. Just wait a minute. Okay. Yeah, so this was it for today's lecture. Okay, so here we have discussed the multiple linear regression analysis, how to estimate its parameters using ordinary least square estimators, what are the estimates, how to calculate those estimates using the inverse of the matrices and all those calculations. Apart from that, how we can find out for those parameters, and also how can we perform the testing of hypothesis, how can we take the decisions theoretically, as well as how can we do all these things practically using R. Okay, so this is all for today's lecture. Apart from this, if anyone of you have any doubt, then you may ask, and the recording for today's session on YouTube. You may access it from the YouTube link, from my channel link. The PowerPoint presentations and the R scripts will be added to the Google Drive. Okay, last day to submit the, so just submit it. And the next session that will be the for this course session for week 12 is on 13th of April and from 6 to 8 p.m. So I hope that people join for that live session, and we'll have a final discussion about the analysis of variance and all those related things related to the regression analysis. Okay, and I think we will bind up the live sessions there. Okay, for the in the next week live session. Okay, so if there is any doubt or something like that, then you may ask. Otherwise, we'll end the session. So, okay, I'm waiting for some time. If there is some doubt or anything, then you may ask. Otherwise, we'll end the session. So I'm uploading these slides. Okay. Meanwhile, if you have any doubt, then you may ask. So I'm uploading this on this your Google Drive. You may access the content from there. Okay, so I've uploaded this tutorial 11 here and the script here 11. So you may access it from there. Okay, so if there is no doubt and if there is no confusion regarding anything, then we will end this session. And hope you will join in the next session that is on 30th of April. Okay, and we'll discuss some more concepts there and do some more examples, and that will be our last session. Okay, thank you guys for joining. Thank you guys for watching. Okay, and okay, we'll end this session now.